Today, we want to continue upgrading our integration thinking to multiple integrals. In the past, we had the integral from a to b of f of x to x as the area under f of x and above the interval from a to b. Mechanically, what we're thinking of doing is taking all the x values from a to b, plugging them into the expression f of x dx, and adding up the results. This is just the continuous version of that process. This gets us around the problem of length times width, where length is continuously variable. It's continuous, so we make a discrete set of delta x's. That takes care of the continuous part, and we flatten out the tops. For each delta x, we just use one value of the function. That takes care of the variable part. Since all of our terms look different, instead of multiplying, we just add them up. We're just doing a continuous version of that. Once we upgrade to a function of two variables, then we just upgrade everything by one dimension. So the integral over some region R of a function of x and y dA will be the volume under the surface and above the region R. Whereas our f of x was a one-dimensional curve above an interval, now we have a surface, or we have a volume under a surface and above a region. In this case, we're doing a similar calculation. We're just doing a multiplication where the function is giving us the height above a piece of area. We multiply the height by the area, and that gives us volume. The integral part is describing a set of x, y that we're going to plug into f of x, y, dA. Everything works the same. It's just going to be, there's just going to be more of it. So this part of the expression this is just a bunch of points x, y. We plug into f of x, y, dA. Same thinking, same mechanics, more variables. That's it. The tricky part for us, the thing that we have to get used to, is figuring out how to write the integral over R. How do we explain to the expression f of x, y, dA? How do we write an integral so that the integral understands the set of x, y that we're trying to plug in? That's our challenge right now. That's the challenge. How do we describe this set of x, y? The new challenge for us is how to describe the region R. When we describe the interval, since it's just an interval, there's only one variable, just x. We just say start at A, end at B, and we're done. There's no shape in that interval. It's just an interval. When we have x's and y's, our region can have shape, and we have to capture that shape somehow. We can't just say start at A, end at B. We have to be able to capture the shape of the region. we are going to do a very similar thing. We're just going to be describing what's x between and what's y between. So it's going to be similar to describing an interval. It's going to be similar to describing an interval. We're just going to say what's x between, what's y between. On an interval, what's x between is the whole thing. It's between these two values. For a region, we have to capture the shape somehow. Let's draw a region, and we're going to just we're just going to describe it for an interval, or for an integral. So let's draw a region. Let's say y is everything between 0 and 2. I don't want to use 2. I want to use 3. I use 3 and 9, not 2 and 4. The easiest thing to describe, the easiest shape to describe, at least in rectangular coordinates, is a rectangle. In this, to describe this region, we just have to say the two constants that x is between and the two constants that y is between. So down here, we see that x goes from 0 to 9. And y goes from 0 to 3. And this is the region I'm talking about. That rectangle is just x goes from 0 to 9 and y goes from 0 to 3. This is what two intervals of constants looks like in rectangular coordinates. It makes, unsurprisingly, a rectangle. Thus the clever name we have for the coordinates. The way this is going to show up in a definite integral, in a double integral, is I'm just going to have two integrals, one for the x and one for the y. So as a double integral, I'm going to write two integrals, one for the x and one for the y. I'm going to describe what x is between. X goes from 0 to 9. Oops, I'm going to include the x equals, just in case you're not color coding the same way that I am. So that first one, that integral closest to the function, I'm going to call that the first integral. That the x goes from 0 to 9, and that's the first dx listed in as part of the dA. Then I'm going to describe what y is between. y will go from 0 to 3. In this case, we would find the integral dx first, and then we would find the integral dy. This is not the only way we could have described this. I wrote this a dx dy integral. What's the other way I could describe this? dy dx. There's nothing that forces me to use dx first just because it's like alphabetical. So I could also describe this with a double integral. I could list dy first, where y goes from 0 to 3. And then I can list the dx second, where x goes from 0 to 9. These two double integrals are describing the same region. The integral part is just telling all the x and y that we're going to be plugging into f of xy times dA. In this case, I've split dA. dA is a little piece of the region, a little rectangle in the region, and I'm breaking it into a length times a width. So the dx dy is the dA. So in the xy plane, I've got a little dx and a little dy that multiply together to make a dA, a little rectangle in the plane. And then f of xy is the height above that rectangle. Those three together, those three factors make the volume. And I just add up all those volumes. The same thinking that we did way back in Calc 1 with Riemann sums. I got it. Oops. I'm doing the usual. Here's x. Here's y. Here's z. I've got some interval dx. Now it's this big, so this is a delta x. I've got some interval dy. The intersection of those is a rectangle, that's dA. Area is equal to length times width because area is always length times width. Anything that's describing area as anything other than length times width is just some niche formula that only works in one situation. It's a specialized tool. Now, up above this little piece dA, there's going to be this continuously variable height, but we ignore that. We pick one value of the function from that square. We pick some point xy in that square. We evaluate the function at one point in that square. That's the height. So above that height is just a function evaluated at some point. That's a length times a width times a height. That's a length times a width times a height. That's a volume. Okay, okay. Yeah.
Is it really kind of using the switch gears to not back and forth or some anti-derivative?
Yes.
When it's defined?
If something is, you mean undefined, like if the function is not defined at some of these values, then we have to integrate around that. Just like if we have a function that goes to infinity with a vertical asymptote, we have to integrate around that problem in the graph. So also, we know that some functions don't have nice antiderivatives. So if this opens up with an e to the negative x squared dx, we can't find an antiderivative there. We have to do something else. One of the things that we might do is to switch those around and look at the dy dx integral. But that's kind of a niche problem, a niche problem that's designed to make you practice rewriting your integrals the other way. Right now, there's no difference between the dx dy and the dy dx because I have the simplest thing possible. X is between these two constants, y is between these two constants. It's very easy to describe a rectangle with rectangular coordinates. It's just two integrals. Let's talk about some rules in setting up definite integrals. Sorry, double integrals. I usually refer to the inside integral as the first integral and the outside integral as the last integral. I could call it second, but you probably know that this is going to become a function of three variables at some point, so there's going to be a middle integral and a last integral. And if I'm feeling extra spicy, there'll be four of them. I won't do that. That'd be too much work. So I'm going to describe this one as the first integral. And I'm going to describe this one as the last integral. So when there's three of them, there'll be a first, a second, and a last. The reason I point this out is that it just sounds weird when there's only two to refer to one as the first and the other one as the last instead of calling it second. I had a car once that only had two doors on it. When you press the unlock button, if you press it twice, it unlocks both the doors. That's how you would say it, right? That's how a normal person would say it. But in the manual, it says if you press it twice, it unlocks all the doors. Now, all is a weird word to use when there's only two. Say both. We have a word for all when it's only two. We say both. You know what I mean? Like if there are only two students in this class, I would be saying like things like both my students. I wouldn't be like all my students. It sounds like I'm trying to make things bigger than they are. But I'm going to use last here, so fucking get used to it, I guess. Maybe the problem is with me all along. The problem is the problem you have with yourself all along. Here's the rule. The last integral has to be written with constants. The last integral only gets to use constants. The last integral has to use constants. This is non-negotiable, except for the times when we're going to negotiate it. But for now, at this point in your career, last integral, always constant. I know it's weird saying this with only first and a last, but the early integrals, your early integrals can have functions of upcoming variables. Pause for copying. The last integral has to have constants. Early integrals can use functions of upcoming variables. This is how we're going to describe the shape of the region. This is where we describe the shape of the region. Now, if this feels limiting because I have to write, say, x is a function of y or y is a function of x, that's only because this is limiting because we have to write things, one variable as a function of the other variable. So if you feel like this is limiting, then that is because it is limiting. But we're doing all this in a function context because we have to start somewhere. Let's start with the easiest form of things. So what I mean by early integrals can use functions of upcoming variables. In a dx dy integral, if I have a dx, this comma is like x so extra. It's intimidating the x. The x was even kind of like leaned away from the comma, as if the comma was like just threatening the x. I have to rewrite this because I'm not okay with this bullying behavior of this comma here. I'll back off, comma. So if I have a dx integral, and that's my first integral, I can integrate this. I don't have to use constants here. I can use functions of upcoming variables. Upcoming variable be y. So this can go, x can go from a function of y to another function of y. I can have g1 of y to g2 of y. I can write functions of upcoming variables on my first integral. But my last integral can only use constants. If things are reversed, I can't just swap and move the x equals g1 of y to x equals g2 of y and have that last, because the last integral only gets to use constants. So if there's another description of this region, if I start with a dy, y can use some function of x to another function of x, because x is an upcoming variable. But in this formulation, dy dx, x has to go between constants. Last integral only gets to use constants. It didn't matter in our first example because we were describing a rectangle. And both intervals or integrals were just over an interval of constants. The last integral only gets to have constants. Early integrals can use functions of upcoming variables. I can still have x's running around after I integrate with respect to y because I haven't integrated with respect to x yet. Any questions? Here's what we need to practice this week. We need to learn how to describe regions. with two intervals. What's x between? What's y between? We need to be able to switch those around. We need to be able to switch, we write our dx dy integral, double integral as a dy dx double integral. Every time I ask you to describe a region, there are two answers, a dx dy and a dy dx. You have to be able to do both. It's like in Calc 2, you could describe a region, a solid of revolution with shells or with disks or washers. You have to be able to do both. You can't just be like, oh, I'm just going to be all shells all the time. You have to be able to do both. I have some problems for you to work on. Now that we're on to integrals, you got some derivatives to find. Like there's three functions of two variables, and I want to find derivatives. We're not going to break into formal groups for this, but we can help each other. We should help each other. That's what we apply this in these problems. That applies to everything. Of course, I guess it doesn't apply to me helping you because that wouldn't be helping, but you get the idea. For those of you playing at home, here are the functions. They all fit on one thing. Oh, they all fit on once. Write your name on the paper, but you will be because you will be turning this in at the end of class on your way out.